My talk's about bootstrapping State and Flink, but I know it's late here on the third day of the conference, so I want to start out with a super hilarious joke that's also very topical. What did the message queue say to Flink? You ready for it? Sad at work. I mean, aren't we all? But why are you telling me that? And the thing to realize is, when you're going to your message queue, the order of the data might not be preserved as it gets over to your data processing engine. But thanks to Flink's event time processing, we can interpret that correctly and reorder it to realize that it should say DataWorks. Huh? Anything? All right, that's the end of the presentation. All right, so a little about me. My name is Gregory Fee. I work at Lyft. I've been there for a few years now. I started out on the ETA team. It's one of the bigger data processing tasks that we do at Lyft. When I started, we were training a new ETA model about every 4 months. And after a little more than a year of effort, we got that down to retraining a model every 10 minutes. So pretty healthy speed up there. Included in that was real-time traffic updates. So that was sort of our first foray into stream processing at Lyft. And as part of that overall project, we created a thing that we call Flight now, which is a large-scale orchestration and batch compute engine. So this is now the basis for most of the large compute tasks that we do at Lyft. I transitioned there into our data science platform team. So this is an overall effort to make data science and machine learning at Lyft easier. And as part of that, I made a custom machine learning library that really helps ease the task of creating machine learning models, getting them deployed in production, doing feature engineering, sort of that tying the whole ecosystem for machine learning together at Lyft. And my current project sort of came out of the machine learning platform work is something called Drift, which is a real-time feature generation platform, which I can talk a little bit more about here. So the need, I think this is a pretty general need, and certainly a need at Lyft, was to have consistent feature generation. So if you're familiar with machine learning at all, you'll know that there's basically two distinct tasks you'll do. There's a training stage, and then there's a scoring stage. And you have to get your feature generation, so basically the input data to your models, the same between those two. And subtle differences between how those are generated can lead to very unexpected results when you get to your scoring. And that can be bad depending on what you're trying to do with your machine learning. So my thought was, well, what if we unify that by choosing just one processing engine that's capable of both batch processing to do the big bulk style feature generation when you're doing training, and then a streaming style engine for when you're doing your scoring online as part of a synchronous service call as part of your overall application. And that's how I arrived at Flink, because Flink takes the unification of batch and streaming very seriously. And so what I've been working on for Drift is to take Flink, turn it more into a streaming platform as a service style offering, making the very simple programs. You give it just a little SQL snippet and it can run it for you, pushes it up into our online serving engine, and makes it very easy for data scientists to create feature generation programs. And there's a lot of automation in there to scale the programs up and maintain them and do all the application lifecycle management. And so now I'm going to talk about bootstrapping State and Flink. So we need to know two things just to make sure we're on the same page. So one is, hopefully you're familiar with Flink if you're in this talk, but just in case you aren't, it's a top-level Apache project. It's a high throughput, low latency streaming engine, so built from the beginning to do streaming. It does event time processing, so this allows you to cast your algorithms in terms of the time at which the event was generated, not the time at which you're processing the event. This can be very important depending on how data is reordered or if you're trying to redo historical processing. It has integrated state management, so you can do stateful algorithms inside of the application itself. It knows how to checkpoint and maintain all this state. It's fault tolerant in case of machine failures. It can support exactly once semantics, which is very important for machine learning. And it's used at a lot of big companies, Alibaba, Netflix, Uber, and Lyft, of course, many others. The other thing we need to talk about is what is bootstrapping. And this is a little less straightforward to explain, so let's go with an example. So the first thing I want to say is it's not backfilling. Backfill is the operation of going through your historic data and generating results based on that historic data. So a typical thing is you have a stream application, it went down for whatever reason, and now you want to say, oh, shoot, I've got a hole in my data, I need to fill in that hole. And so you can go through your historic data and process that result, put that back into your data lake. So you can sort of fill in the hole that was missing there. Another common task is that you've generated some new business logic, and you want to see what the results would have been on your historic data. So then you can do a backfill operation, generate that data, and store it. So that's backfilling, not bootstrapping. What's bootstrapping? I think maybe it's easier to use an example of what is bootstrapping. So this is a little, I'm not actually sure if this is valid Java, but this is just a simple application. I think it comes out of one of the Flink examples of counting the words in a string. And the important part to see here is there's this window of 7 days, and so we're going to look over 7 days worth of data and report a new count every hour. Right? So this is a sliding window. And so you make this application and you launch it, and you kind of go through like the 7 stages of grief, right? You launch it, you feel like a boss, you've shipped your program, and then you're waiting though, right? Because it's the 7-day window, so you don't have all the data yet. So your count that it's producing is not actually producing anything until you reach the end of that window. So you go through like anger, and then you're just bargaining like, please just start producing data, and then you finally 7 days are up, and you feel good, you got your results, and then you realize they're wrong, and you have to go back and change your program, and then you were going to wait another 7 days, right? So this does not help your velocity as you're doing your development. And then there's an even worse problem, which is here's a pretty simple piece of SQL, and this is one of the first features I was asked for when I started this project. This is just let's count the number of rides a user has done on the system in the history of Lyft. So we go back to 2013. So there's lots and lots of rides now. This is a pretty big problem, but the issue is if you start this program running now, it's never correct, right? You don't want to get the results from here forward. We want the results from the beginning. So this is a real bootstrapping problem of how do you get the data from history into your application and then dovetail that into the streaming program. And that's exactly what bootstrapping is. So bootstrapping is taking data from your historic store, using that to seed your program, to bootstrap it up, get up to the current time, and then move forward. And you get, and the real advantage of this is, one, you start getting data immediately, or as fast as you can get through the historic data, but two, you can support these types of things where it's like all data in history, and then start getting the results in real time. So a couple of things to consider before we start talking about like solutions or ways to do this. One is about provisioning. So if you're familiar with how you might attack big batch style problems, you typically have like large clusters to do this. You want to have as much parallelism as you can. And you sort of want that for bootstrapping too, because you may be going over a lot of data. But then when you get into your real-time processing, there's typically a lot less data. You might want a lower provision thing. And at Lyft in particular, we care about sort of the cost of all this because we're thinking about running thousands of little feature generation programs. So the provisioning required for each sub-application of this is pretty important. It adds up pretty quickly. Some other things to keep in mind, or that I kept in mind when I was looking at this, is that generality is pretty important because, as I said, we're looking to have like thousands of these little applications. So anything particularly application-specific is going to make it a challenge for us. We don't want to have multiple different types of solutions across the different applications and have to choose one. Another is that we are looking to get this into production pretty much immediately. So try to slant towards things that we know can work and that will be stable and that we can maintain. And so, of course, this is what I did for Lyft. Not necessarily the most applicable thing to you, but I'm going to run went through various options. So hopefully it captures something that's good for you. So the first solution to bootstrapping, this is the best one. If this works for you, please do it, is to use the stream retention policy on your whatever your stream system is. So if you're not familiar, the streaming systems, they are streaming your data, they're giving it to you, but they also keep data for some retention period. And this is handy for like if you have outages and things, you can sort of catch up from what has been played already. So Kinesis, if you're on AWS, has a maximum 7-day retention. So if you're bootstrapping 7 days or less, this is great. Just please use it. Kafka, there's no inborn limit on how much retention time you can have, but it is like very expensive to hold data in Kafka, and it's not really designed to have like petabytes of data in it. So there are some real limits in there. But again, if it's feasible for you to do bootstrapping just by looking back at your stream, then this is by far the easiest, most maintainable way of doing this. And so touching on how Kafka can be expensive with a lot of data, I thought of this idea for like an infinite retention in Kafka, which is instead of just using the sort of primary storage for Kafka, which can be expensive, allow there to be a secondary storage where as the data grows and as you reach some sort of cutoff dates, maybe you move the data out of primary storage back into a cheaper secondary storage. And this can have like different characteristics about like speed and stuff because you're probably not accessing this data nearly as often. And so this has the advantage, it can pretty much give you infinite storage. If you're against S3, it's like effectively infinite. And you know, there's a fairly mature set of connectors around Kafka. So, I mean, Flink's Kafka connector is good. It also would allow you to bootstrap other things if that's important to you. The disadvantage, you may be getting different performance characteristics. You have to think about that in terms of what it means to be pulling from primary storage versus secondary storage. And what I talked about before about the provisioning of like, you know, you want a high provisioning when you're bootstrapping, and then you kind of want to go to a lower provisioning when you get to the real-time, you're just doing the real-time data stream. There's no real easy way to like reconfigure your Flink job. There's no message that happens like when you reach that state. So you have to figure out how you want to reprovision your job when you reach that state. But the biggest disadvantage is that this does not exist. So you'd also have to go build, this. But there's some other projects, Apache Pulsar kind of provides something along these lines. Pravega does as well. Those are sort of newer technologies. There's not as much ecosystem around those, but if the ecosystem works for you, then these are probably worth checking out. So now we're gonna take a step up the stack. So going away from your stream provider up into the source of your Flink. So the idea here is, what if we could write a source that would bridge between our stream source and our historic source? So the idea here would be, okay, I can look back at historic data out of S3, and I can say like, okay, let's generate messages saying like, okay, read this file from S3, read this next file, and sort of go back in history, coming forward, and then when you reach some sort of cutoff point, you're going to go to your live data, then cut over and start saying, okay, now read these Kafka partitions, right? And yes, at Lyft, we do generate all of our message and data on scrolls, as you can see. Everyone's asleep. It's good. So the advantage of this would be that like now you don't care if you're on Kafka or S3 or whatever. You control the source. You can work against any stream provider. You can work against any secondary storage. The disadvantage is writing sources is actually pretty hard. I don't know how many have tried it. Getting them correct, getting them to perform well is pretty tricky. And in particular, like this point where you're going to bridge between the two data sources, it's pretty tricky to get that right and make sure that you don't have any duplication of data across the two different data sources. And again, this is another solution where there's no particularly like distinct place where you could say like, I'm done bootstrapping, and therefore change the provisioning from like a highly provisioned state to a lower provisioned state to process the real time. So this one I didn't actually pursue. Instead, what I did is I came up with the idea, yet one more step up. So like at the application level, let's divide the world into two stages. I'm going to have a bootstrap program, which I'm going to provision very high. It's going to read data out of my historic store, out of S3, process it through the business logic, wait for all that data to get through there, process it all, and I'm going to trigger a save point and cancel that program. And I'm going to run a second job, lower provisioned, and it's the same shape of job. It's just the source is going to be Kinesis in this case. It's going to start from the save point that I just created, and then it's going to start processing that data. So the cool thing here is I get to provision different jobs. I use the save point to take the state from the bootstrap thing and move that forward into the live program. And I don't have to do anything tricky. There's no low-level stuff. It's all application level. It's fairly easy to get correct. And let's find out if there's any disadvantages here. So this is sort of an image of how you may think about this. So 2 programs, S3 source to business logic, and then syncing out somewhere, wherever you want to sync. I'm syncing out to basically Dynamo. And then the second program, Kinesis source, same business logic, and it's still syncing out to Dynamo. But how do we make sure we don't get any repeated data between these two? We need to ensure that. So in the awesome Lyft Pink here, I added in some filters. Let's just specify a target time, which is going to be the bridge between, or the indicator between when it's bootstrapped and when we start reading the live data. So this takes advantage of the retention time that you have in Kinesis. You just have to choose anywhere within the time where you have an overlap between your historic data and your stream retention data. Choose a time in there. So you process up through S3 until you hit that filter. And then you push that all to the sync save point. And then Kinesis, you just go through and throw away all the data before that timestamp. Once you get to that timestamp, then you start processing that data. OK, but how do we know when the bootstrap is complete? So for that, we've got a little trickier. So here, what I do is from the source, it's reading through the S3 source, and then it pushes through a special message saying like, I have reached the end of what you wanted. And then on the other side of the sync, there's a termination detector. So that's looking for that special message, and then it says, cool, everything's been processed. Now I can terminate the program. And so what the termination detector actually does is it calls back through Flink's REST API to call a save point and cancel the job. And then there's some other automation that sees that, and then it starts this second job here with the Kinesis source that picks up that save point. So what did I learn by doing this? So it's possible to automate Flink from within Flink, which I thought was pretty cool. But it is a little fragile. So this special message that I'm pushing through actually takes the form of a watermark. And I don't know how much time you've spent with like processing watermarks and maintaining watermarks. There's a lot of subtlety involved in that, and it's easy to get it wrong. I'd end up with a program that didn't end up terminating, and I didn't know why. And it's fairly challenging to debug all that stuff. And sometimes I'd break it, and I wouldn't know why. The other is that the save point logic is by UID. So that what a UID is, if you're not familiar, is you assign some sort of name to each of your operators in Flink. And when you do a save point, it uses that UID to then map back when you read that save point to make sure it gets back to the same operator. The problem is I want mine to be based on SQL, and the SQL engine in Flink does not actually assign a UID, allow you to assign your own UID to each of those generated operators. So you have to depend on the application having this exact same shape. And this is sort of a potential maintenance problem. So I didn't end up liking this solution. So I created another attempt at this. So this one, it's still 2 jobs. So we have a high provision job, we have a low provision job. But the difference is I'm going to read from both data sources in both jobs. So the first job, you're going to read from S3, you're going to read from Kinesis, you're going to union those together, push it through your business logic, and write out to S3. And we can just, since that program's already reading from both data sources, we can just let that run forever if we really wanted to. But because it's more highly provisioned in order to get through the bootstrapping in a reasonable time frame, for cost savings, it's nice after the bootstrap's completed, you can just come along and do that save point trick again. So you hit the save point, get rid of that job, bring up another job, same shape, but lower provisioned, lower parallelism, restore from the save point, and then you go forward from there. And that works because there's no more S3 data to process. So everything runs fine. So here's the same sort of style of diagram for this job, and you can see it's just we use the target time trick again to make sure there's no repeated data. Go through the same business logic, push it out to the sink, and both those jobs have that same shape, just different levels of parallelism. So this is great. It's a lot less fragile because it has exactly the same shape. There's no different sources. Everything is exactly the same. So this one actually does work with SQL in its current form. The disadvantage here is that you either have to run that one job that's very highly provisioned, or you need some sort of external automation to say like, oh, look, we've reached the bootstrap point where bootstrapping is done, and therefore let's do that save point and replace trick. The other disadvantage is because of how the watermarking works, if you have any windows in your data or windows in your algorithm, the entire time that you're doing bootstrapping, you're reading the data from S3. The Kinesis source is pushing all that data into the system, and you end up buffering all that data. So depending on how long your bootstrapping takes out of S3, you could end up buffering a lot of data in there. So that's very dependent on your scenario, but in practice for me, it hasn't really been a big issue. And so this is actually what we have in Lyft in production right now. So that's an actual diagram out of the running system at Lyft, and we're adding more programs as fast as we can at this point. So that's a system that works, but it's not really optimal. I think there's a lot more we could do in this. So I already mentioned sort of the Kafka infinite retention idea. So that doesn't exist, but it would be great if it did. And keep in mind, like, there's a lot of other subtle problems in there in terms of getting good performance, like how you might repartition the data between like what it means to read from a stream program versus read from a batch program. There's various different trade-offs, so you may want to repartition the data differently between those two scenarios. Another idea is when I talked about that source solution, one of the problems is sources are pretty tricky to get right. But and in part that's because you write sources outside of the normal sort of Flink metaphor, or outside of the streaming metaphor. If you could instead like write a source like this using Flink's programming metaphors, where you don't have to worry about as many things, that can make writing that source a lot easier. Beam actually has something called splittable do-fn that sort of goes down this path. So that might be an interesting thing to explore in the future in sort of Flink's API. Another idea is to do that could help with this is dynamic repartitioning and adaptive resource management. So what that means is instead of having two different jobs and having to like do the save point trick and then replace that with a second job that's lower provisioned, allow an API in Flink itself to just say like, hey, let's change the parallelism from like 1,000 to 100, right? Just be able to have Flink dynamically re-provision the parallelism. And another thing would be when you're bootstrapping, you might not care as much about checkpoint and how often you're checkpointing, because you could always just sort of fail and recover. It's not necessarily the most timely of tasks. Versus when you get up to your real-time processing, you may care about recovery time. That may become sort of a key feature for you. And so you may want to have different checkpoint policies, because the more often you're checkpointing, the slower your application can run in some cases, although Flink's checkpointing is pretty good. A final idea is around meta messages, so that the solution I described where I was using a watermark to sort of like trigger the termination of it, that ended up being kind of fragile, because watermarks have a semantic, but it would be really cool if there was a way to sort of along the way in your stream push a message that's not data itself. It's an indicator of something, and have that flow through in the same order that the messages flow through, and you can trigger different behaviors based on that. So like that might make the mechanism where you're trying to like send that termination message through the system less fragile. And now you may be thinking like, this seems like it was all streaming mode. What did you think about batch mode? So yeah, batch mode is cool because if you do know you have a bounded data set, there's different algorithms you can use. You can be more efficient. There's like a lot of optimizations available to you in that case that aren't available to you when you're doing an unbounded data set. So a couple of ideas that we could do around how to take advantage of this batch mode processing is, one would be start off Flink in batch mode, process the historic data, and have the output of the batch program actually be a save point. And then start a second job that's now the same algorithm in streaming mode, pick up that save point, move on. So it's sort of thematically similar to some of the other solutions. Another idea would be to have Flink itself have sort of special knowledge of how to do bootstrapping. So here you'd start out using the batch mode algorithms and then have some indicator in there that like Flink actually understands, and it says like, oh, okay, now it's time for me to build up the data structures to do the streaming style of this same algorithm and then push it forward. So the unification there around SQL sort of potentially allows you to do this style of transition. So yeah, sort of summarize like what did we learn here? Lots of stream programs are stateful, and if it's stateful, you probably could take advantage of bootstrapping instead of waiting. Like go ahead and just like use your historic data to get yourself up and running faster. And it's very possible on Flink, but there's many ways we could sort of improve this. So I'm hoping we can sort of continue to work in this area and get some better, more general solutions. Any questions? Anyone still awake? Nothing? I bored everyone. I've got a question. No, okay. All right, well that's it then, I guess. Oh, we have a question. There's a microphone if you want, but.
Are you running Flink on Yarn or Hadoop tree cluster or by itself?
So the question is, how are we deploying Flink at Lyft? We're currently deploying it right onto raw EC2, and we are in the process of adopting Kubernetes and deploying it on Kubernetes. Yeah, okay, so hopefully most people heard that because he's in between, everyone's in between me and him. So the general topology is we're collecting sort of event data from many sources, so it's phones and the services within Lyft. And we collect that through, it's a Kinesis shop right now, so everything gets pushed through Kinesis, and that's basically our primary source. And then for historic data, the Kinesis gets fire hosed out to S3, so that's how we bring that back into the system. That's right. Yeah.
So in case you have two different streams and the result registries out, they require also messages and different kind of journals. And let's say they might have different timetables. Right? So in case they come at different time, how do you deal with it? I understand from Bootstrap, you are able to spend a bit more time when messages still come, and you cannot reduce output.
Yeah, so that's a good question. So we're doing all of the processing in event time. So the difference between the sources of whether it's real-time data or whether it's historic data kind of start to go away at that point. And we basically treat all of the inputs as streams. So even if it's when it's coming from S3, it still just looks like a stream to the system. So the fact that it's not actual real-time live data sort of is gone. And then at that point, you're just talking about Flink semantics around how do you do windowed joins. It's a time-bounded join basically between the data. Does that answer your question? Yeah. So I mean, you basically have to read the data from all your data sources, and then you're going to do the join. It's completely dependent on Flink's join semantics around how you establish the window around in which the join happens. We honestly don't really have any joins that we're running in production right now because joins are a little bit tricky. But yeah, it basically, like, there's no special semantic around what you'd have to do to bootstrap for a join, as long as you treat everything like it's a stream and like it's live data, and you use event time processing.
So for example, currently, if I log in into Lyft and I want to see the number of times I'm connected or I've taken a Lyft, it will be running through Flink, or is it stored somewhere and given me after?
Right. So the question is, like, if you logged into Lyft and you want to sort of like see any of the stuff that's calculated by this, how does that happen? So the overall topology, so starting from what the other gentleman asked, like, so, hey Dan, what Dan asked was, so there's a bunch of input data that's coming from like the phones and from the services. We collect that through Kinesis, we process it through Flink like this, and we push it out to something. So right now our target is all machine learning, and so we push it out to something we're calling feature service. So that's really just a key value store. So yeah, so we end up pushing all the data, syncing all the data out of Flink into a key value store, and then that's how things are accessing it for online usage.
In fact, the time I log in, it's already starting to process.
Sorry?
So when I log in, the process, this event has been already pushed.
That's right. So you're always just seeing the latest output, which is typically a few milliseconds old. Right. So basically, if you're familiar with Flink's fault tolerance strategy, it's all around checkpointing. So the S3 source that we have written does checkpointing appropriately. The checkpointing can be like, when we're doing the historic reads, the time between checkpoints and where the checkpoints happen is actually fairly broad. So the recovery times are not what you sort of in the same category that you'd get for like when you're sort of checkpointing out of Kinesis or Kafka. But the idea is basically like, we happen to have a time window of a day for a lot of our historic data. So when you do take a fault, you're going to fall back basically a day and then start to reprocess from there. But Flink basically takes care of most of the heavy lifting there. Of the checkpoint is snapped basically per day, and you're just going to fall back to that. It drops all the data because Flink does all the state management itself. So you're just rolling back to that last checkpoint. Everything reloads from that point, and then you just push forward again. Right. Yeah. So yeah, currently we don't do a lot of machine learning algorithms on the device itself, mostly because like the iteration speeds that we can do on the server side are much faster than how often we can release the client app. And doing experiments and stuff is a little bit more challenging when you're trying to do client-side detection. We do have plans around, like, the question you're asking in particular is around my work on ETA and how we did real-time traffic updates. That work in particular, doing routing, doing efficient routing, you need to have a global view. So it's basically not really possible to do efficient routing from the client side. Sweet. Thank you, everyone.